Okay, so once again, welcome to our member webinar. Quick summary of logistics for those who need it. So the turning off your camera is actually not relevant for this type of session. The way we've organized this session, you can't turn your cameras on anyway. When we run this as a traditional web conference, we remind trainees to turn off cameras, but this is such a big event, we have to run it with a different mechanism. Questions are welcome as we go. You have the Q&A in the chat if you've joined via Zoom, and we have a couple of people on hand in the background who will try and copy questions from the YouTube feed into the Zoom session so that I can see them. I will have a little slot and ask for Q&A at the end, depending on how much time we've got available. But you can certainly ask relevant questions as we go. We have links to the slides. It's the top one that you want, unless you have problems accessing Google services. I hope that will be dropped into your chat very shortly, because trying to type the hex number is going to be very difficult. But that gives you access to slides and downloadable exercise material that you can do after the course. So a very short biography of myself. This is as much as anything to help you understand my prejudices, where I've come from, what my background is, so that you can decide if what I'm saying makes sense in your applications. So my background was at ST Microelectronics, where I joined what was at that point a toolset team, back in the day where tool sets for microcontrollers used to come with real-time operating system built in, and the C library and operating system were very tightly integrated. So I joined as an operating system engineer, but in a toolset team. And as the set-top box industry that ST worked in at the time pivoted from traditional RTOSes to GNU Linux, I followed on along with it and have been working on GNU Linux for not quite 2 decades, but getting close. During the following years, I've worked across most of what you can do on a set-top box, with the possible exception of the security coprocessors. So I've done software stack architecture, networking stack, audio, video, and then right down to low level to things like C libraries. Back in the early days when I was in the toolset team, I would dive in the C library shop. Finally, as at ST, I came in as a tech lead to try and keep a driver project on track. It was a new driver stack that was being developed at the time. And that was the point at which my role firstly became largely consultative, supporting and helping other team members who were trying to get to grips with the stack that we'd been working on for 5 years previously. And that's why I kind of got interested in training and mentoring. Switching to that consultative role is what probably leaves me standing and talking to you today. And then at that point, I switched to Linaro. I spent a year in the kernel working group, and then became the tech lead for the support and solutions engineering team here at Linaro. So we have a very varied role, but everything that I do is kind of centered in that background I have in tools and operating systems. So that's me, and that's where I've come from and why I'm talking to you today. So here we have the outline for today's course. Most of today, we're going to be talking about user space and some of the real-time traps that exist if you get the APIs incorrect. And then the following week, we will move on to what the kernel can do. So to start off with, I'd just like to give you a quick visualization of the development of the classic RTOS and how it would differ from the same system built with a Linux kernel. So we have our hypothetical real-time system built using a classic RTOS, where there is no separation between user supplied code and the kernel. So everything essentially runs in kernel mode. We have the 3 greenish boxes towards the bottom. So scheduler, memory management, and any networking is almost certainly going to be built into the RTOS. The RTOS may well have some drivers built in, but there will be a degree of user supplied gray drivers as well. And at the top, we have the user supplied components to make the real-time system. So we're building the real-time system fundamentally out of these control loops. So this particular real-time system, I like to think of it as industrial control, perhaps some kind of gigantic paint stirrer or something like that. So the control loops are there to ensure that whatever industrial process is being worked is held at the right temperature, it's being stirred adequately, whatever else we need to do to maintain the large thing. It could equally actually apply to drones. The control loops are drones are very much faster and shorter, but if you have anything involved in flight stability, things like control loops can be very valuable for that as well. So that's the fundamental real-time aspect that controls whatever real-time process we're having. That's where most of the deadlines are. And then as we go to the right, we have things that are more to do with command control, status reporting, configuration, and communication. Oops. So we have some module that provides local user interface. And inside that local user interface is the big red button that can bring the system safely to a halt. So that's the little red dot as well, to remind that we've not just got status panels telling us what temperature things are at and allowing operators to see that they're happy. They also have the important intervention to bring the thing to a halt. Incidentally, you don't have to view this as safety critical necessarily. The consequences of failure to control industrial things can just be the loss of a lot of money, as your industrial process doesn't produce the right output and you waste half a ton of plastic. The degree to which you would do safety critical, we're not going to discuss because it's an in-depth topic in its own right. We're going to talk about real time. So we're assuming here that we haven't got to build up to kind of automotive levels of safety criticality. There's a module that kind of does control and status reporting. That provides information on what the control loops are doing. It allows you to set the goals for the control loops if they change over time. And then finally, we have some communications on the right. So we have a web server, which we assume is going to be used for configuration. And we've actually put in some mesh management as well. This is actually not entirely uncommon in factories because it's difficult to run wires across it. So sometimes the nodes do talk to each other. But it also gives us some talking points as we move towards the Linux world. And just the most advanced RTOSes did bring in separable user space components. So you can see over here, this is an alternative version for an RTOS with processes, where we've taken the things that are either network facing or don't have any component other than just reporting things to the user. And we've hoisted them up and we've put them in a separate process so that if there was a mistake in that piece of code, it couldn't take down the rest of the system. You'll note we've kept the big red button separate, and in the kernel at this point, we've had to separate them out because of the additional real-time component, if you like, to a safety button. You do want it to react in a particular period of time. So that's our hypothetical system. And then we have what you might call the proof of concept. So the proof of concept for Linux is basically taking the existing RTOS application that used to sit there in the kernel, bring it up, run it in user space, and use all the kernel features to talk to the drivers, the scheduler, memory manager, and everything else. So this is essentially a prototype, and it's a prototype where you've taken your code for RTOS, you've made it into a single user space process, so everything still connects to everything else as it did when it was in the RTOS, and we start fiddling with it. And you would never knowingly design a Linux project like this, but if you have an RTOS legacy, this is one of the ways you can start to develop away from the RTOS legacy in smaller stages. But this is not a natural way to build a Linux system. A Linux system would look perhaps much more like this. So this is still user supplied code, all above the top, but we separate it out based on the role. So the control loops, we've put in a process with all the control loops and the control and status reporting, which is interacting with the control loops, looking at their targets and things, and their measurables, all in one process because they sit quite nicely in that sense. And we've separated out the local UI with its big red button, the mesh management, and the web server. So this is now much more how you would build a Linux system, with one exception, which is what I'm showing you here. Is still based on the we build everything view of the world. And most people have come to open source and to Linux in order to benefit from off-the-shelf open source components. They help us drive down the costs. Oh, there's one subtle change made at the bottom as well, which is the less grey when we've gone to a Linux system, because typically Linux comes with an enormous number of drivers out of the box. So the number of drivers you have to supply yourself are likely to drop. This is what we might call the better structured Linux system. We still have the control loops, the control and status supporting the local UI. We've separated out the big red button because it sits in a different real-time aspect. So we might want to run parts of the big red button at real-time priority. We might not want to run the local UI at any kind of real-time priority. And then on the right, we've taken benefit from off-the-shelf software. Once you have got your correctly structured Linux system, one of the steps you might do with it is to recognize that I don't need to have a proprietary or licensed HTTP server that I picked up from my RTOS. I might actually just want to bring in an off-the-shelf Linux component. We've used Apache in this example, but it doesn't really matter. Likewise, that mesh management that was probably in a traditional RTOS licensed from some kind of communications stack vendor, we can replace with an equivalent open source daemon. And that box on the right is more than anything the reason that people are being attracted to Linux. It's being able to run not just real time, but the non-real time activities using off-the-shelf components. So a quick summary of what I've been touring you through. Firstly, the system I've shown you does have significant mixes of real-time criticality. There are very timing critical components in the system. The control loops, for example, are going to be extremely timing critical. If you don't if it's a simple PID controller, for example, if you don't run the cycle of the PID controller, which involves observing the measurable and then adapting the control surfaces at a particular speed, you'll get oscillations in the control and you won't get such precise or high quality result. As I've mentioned, the big red button within the local UI does want to be reacted to in a certain period of time. If a user operator is hammering a button saying stop this machine, you do want to make sure that that is more important than maintaining the mesh network. It is possible that controller management could involve real-time constraints, assuming that we don't rely on mesh networking to do that. I mean, obviously, mesh networking is not going to be very successful if you've got real-time constraints sitting over the top of it, unless it's very, very carefully constructed. So we're assuming that at the moment that the network is not in scope for this machine. You can build systems where the network is in scope. It's much more difficult to use off-the-shelf components at that point. And we're clearly assuming that the HTTP daemon, the local UI, the network in this case, are not real-time. So that was one of the messages. The other is that by switching to GNU Linux, if you're moving from a classic RTOS, one of the things you are looking for is ways to replace in-house or licensed implementations of commodity software with off-the-shelf open source alternatives. It's a way to reduce license costs or maintenance costs. So we step into Linux at this point. So I have a quote up here from a chap called Doug Niehaus, who was I don't know if it's a friend or colleague of Thomas Gleitzner, who is very influential in the real-time world. But it's an important statement. The real-time is not about running things as fast as possible. Turning on real-time features generally reduces overall system performance. Real-time is all about running as fast as specified. It's saying that if I have a control loop where I have to read a measurable and manipulate the control surfaces in a specific millisecond within a 10 millisecond window, that every 10 milliseconds I get my 1 millisecond of runtime every time at exactly the right point. It's about ensuring that we complete that task at the point we were supposed to do every time. It's deterministic, but it doesn't actually matter to system performance whether you service that, if you manipulate that control surface in the first 25% of that millisecond window or at the very last microsecond. Providing you have manipulated your control surfaces a millisecond after the window opens, then the real-time specification has been met. The actual performance of the system, providing it meets the specification, doesn't matter in terms of performance as in how fast you achieve something. It only has to meet the specification. And the key thing about working with Linux starts life as a general purpose multitasking operating system. And it is usually still used in places where that general purpose character retains some utility. Classically, people have switched to Linux to get extra features. They wanted the Samba server so they could interact with Windows machines more easily. They wanted, so I don't want to give all set-top box examples, but the Samba server was definitely a big attraction in the set-top box world. Yes, and many of the new general purpose features are not real-time. The real-time is the original mission of the box, the presentation of audio and video, or the manipulation of those control surfaces. And we've added features to it by introducing Linux. And that implies that in the vast majority of real-time Linux systems, it's very important to understand which parts of the system are real-time and which part are not real-time, which parts are essentially inadvisable to try and elevate to the real-time world. It's a very significant trap for people who've been in RTOSes forever to want to set the priority of everything, because that's what they're used to. They're used to saying, well, this task is more important than that task, so we'll give it a higher priority. But if neither are real-time, then neither are real-time. Don't make them real-time. Use the real-time for the real-time aspects and make sure you know which parts are not real-time. And then finally, Linux can be configured in multiple ways to choose a correct trade-off between best system performance for the general purpose parts and the worst case latencies for the real-time parts. And that's what we'll talk about almost the entire of next week. So this week we're going to be talking about the interfaces that allow these top components in the user space to be well integrated into the system. And next week we'll talk about these different ways you can configure Linux to get an appropriate trade-off in terms of system performance. So having kind of suggested to you that we want to have this strong, clear understanding of what's real-time and what's not real-time, we now want to start thinking about what features Linux provides. And ultimately what it provides to us is multiple schedulers. It's not just one scheduler. There are actually 3 user-facing schedulers that we can use to cause our tasks to run. And this quite often is a difference from a traditional RTOS, which would simply have the single real-time scheduler. So roughly speaking, we have the real-time scheduler, or perhaps the deadline scheduler for real-time workloads, and we have the completely fair scheduler for non-real-time workloads, which we'll come to in a second. So different terminologies exist for real-time. I think as much as possible, I'm going to try and use this terminology that we've got here. So at the point an event is detected, which can either be a piece of hardware asking for service, or of course it can be a timer elapsing if you've got a time-based real-time goal. You know, a vertical sync happens every 20 milliseconds in the UK or 16.7 milliseconds in the US. And although it's an interrupt request, it's basically a timer when you think about it. Similarly, for feeding any kind of streaming system, audio, video, continuous streams of sensor readings from industrial systems, they're actually time-based. Whether the hardware is raising an interrupt or not, the fact that the time is completely predictable, it's happening at a particular time. Other times you can have reactions to things. You know, hardware requires a service because it's bursted out a bunch of stuff, and we have to refill its buffers before things can underflow. That, depending on what controls the pace of transfer, can be an event, but quite often the event is actually time-based. And then we've got some processing to do on the CPU to satisfy the event. So there is a delay before it starts, the start time. There is a time it takes to complete. So completion time can be odd because it doesn't necessarily mean when your interrupt handler stops running. It's the point in the interrupt handler where you've met the real-time goal. Once you've completed, if you've completed before your deadline, which is what you want, there may be some slack time afterwards, which is when you've run faster than was necessary to meet the specification. That's fine. Slack time is important and necessary to give your design some resilience. And then finally, you have the deadline, which is the point at which the process must have completed responding to the event. And obviously, if you miss your deadline, that's the equivalent of having a negative slack time. And that's the point at which your system has failed. It has not met its real-time constraints. It's not met its specification. Your system has failed. It may be able to recover itself, I mean, my background set-top box, if you don't get the frame on display on time, it doesn't actually, it's not a recoverable problem, but it is a quality of service fault. You know, some customers have specifications about we can only do that once every 24 hours. And if it's audio that gets interrupted, it's actually physically uncomfortable as well. Getting clicks into your headphones is actually physically uncomfortable. So in the set-top box world, real time was about quality of service, not about somebody failing to be hit by a big metal arm or something like that. But it is still there. It's just the consequences of failing are not as severe. But they were real because we were measured by the purchasers against quality specifications that they were quite strict on. Okay, so we're going to start off by looking at these different schedulers we have available to us to schedule work. So the scheduler classes, there are actually 5 scheduler classes in the Linux kernel, but only 3 of them are accessible to user space. The other 2 are special cases that we'll talk about next week. So the schedulers available to user space are the normal scheduling class, which is all the variants of the non-real-time scheduling. We have priority-based scheduling class, which is basically a highest priority gets the CPU scheduler. So if you have a higher priority than the person already on the CPU, you will preempt them and you will take over the CPU almost unconditionally. And then there's a earliest deadline first scheduler, which I'm going to display when we have the drawings because it's probably the hardest to understand. So normal scheduling. This is all schedulers that are based on the completely fair scheduler, which is basically a form of weighted fair queuing. So the fairness is weighted, and obviously weights make it unfair in the sense that you can have processes that are receiving an unfair share of the CPU. That's the weighting. But after you've accounted for the weighting, it allocates the CPU resources equally to all things that are demanding CPU time. And in particular, the thing that makes completely fair scheduler so useful and well balanced is this concept that sometimes is called sleeper fairness. If you've got 2 tasks competing for the CPU, and one of them is asleep half the time waiting for input, that doesn't mean that it's giving up the CPU when it goes to sleep. And the reason this matters is think about your text editor. What a text editor does is it sits there and waits for you to press a character. When you press a character, it's really helpful to get the glyph on display as quickly as possible because it makes the human who typed the character feel more comfortable. It's a form of real time, ultimately, if you get really technically into it. But it's one where humans are so bad at perceiving the quality of service that we don't normally consider this to be a real-time task. There is a loop by which I press a button, I see it on the screen, and provided it's fast enough, I feel happy as a user. And CFS ensures that by this sleeper fairness, because your editor, when it is asleep, is not using the CPU, but it has a right to use the CPU. It has a right to a fair share of the CPU, even though it's asleep, which means the moment you press the character, it's very likely that that editor has a fairly high effective priority because it was behind compared to compute-intensive tasks. So when that interactive task that was asleep receives the key press, because the competing tasks, the CPU-intensive tasks, have already had a very nice slice of the CPU, it will almost certainly be one of the first things to be run. And that means that flows right through the X server, display server, up to the screen. All those components tend to spend a lot of their time asleep waiting for something to happen. And that means that you get, when you press the key, fast paths to all these different processes that are responsible for getting that glyph on the screen. And it gives a comfortable experience for the user whilst allowing compute-intensive tasks to soak up the rest. This also fits into things like the HTTP server in our example. So not only the local UI, HTTP servers similarly spent most of their life asleep waiting for network packets. Again, they will get nice, fast, interactive responses as a result of the normal scheduling processes in Linux. And this is the reason I say that you want to make sure that non-real-time stuff is put on this scheduler where the heuristics behind the completely fair scheduler, they're not actually heuristics, the measurements behind the completely fair scheduler will almost always do a good job for non-real-time activity. And where it doesn't automatically do a good job, we can affect it with those weights that I mentioned. So the weighting that we have in our fair allocation of CPU is weighted by this thing called the nice level, which is a very classic Unix concept. I'm going to work really hard in this presentation to call it the nice level, because it's not a priority in the same sense that a real-time priority is. It's a weight on how favorably or unfavorably the CFS scheduler treats the process by allocating a weight. So there's a couple of APIs that you can use to manipulate it. We have the nice call. There is actually a thing called set priority, which is quite confusing because it doesn't affect the priority, it affects the nice level. But ultimately, the result is that if you have a process with a nice level of -20, which must be owned by root, incidentally, you can't elevate nice levels typically above 0. It's actually controlled by this R limit, but the default for the R limit is that you can't elevate your nice level above 0. So user space processes can make themselves nicer to others, but they can't demand and run higher than typical processes. Once you have root, you can actually make your processes very highly favored. So something with a nice level of 19 will be very nice. It will get a tiny slither of CPU time if it's competing against other CPU intensive processes. But if you have a CPU intensive process running at a nice level of 19 and there is competition, it will get a very tiny slice of the CPU. If you set it, if it's running in the background and there's no other competition, it will get the entire of the CPU. So if you have opportunistic background calculations, like transcoding of video formats into something that we can push to a tablet or something like that, I have to admit, in the example real-time system we have, there aren't any compute intensive background activities. So I don't think there'll be any case for nicing anything up and down in the exemplar that we've used. But where you have compute intensive background work to do, like I say, transcoding is quite a common one on media devices. We can set it to 19 and it should not affect the user experience by running in the background. And so within the normal scheduling class, there are 3 different policies, which are very, very closely related. They all use the same algorithm. We have shed other, which is the default, so much so that it's actually referred to as shed normal inside the Linux kernel source code. But when you're in the user interface, the user space calls it shed other. All the normal scheduling classes run at a static priority of 0, so they all have the same effective priority, which is the least priority compared to the real-time classes. And CFS effectively provides different threads with ever-varying dynamic priorities based on their previous CPU consumption and their nice level. And it does result in fair progress among all the shed other threads. If you had 4 processes competing and none of them sleep for more than 75% of the time, they will all consume equal slices of CPU. And it is very much the same default. For every workload that you can't express a deadline, you can't express the relative importance of, you should be setting them to shed other. You don't mess about doing real time for non-real time components. There are a couple of other more exotic scheduler classes based on CFS. I will mention them for completeness, but they're seldom necessary. Nice levels provide sufficient. There is this component called shed batch, and that is exactly the same as shed other, except that when they choose to sleep, some of the calculations that take place at the point they choose to sleep are skipped, which means that the scheduler believes they consume slightly more compute time than they actually consumed, which causes this mild level of disfavoring of them in scheduling decisions because they're always assumed to have used the whole of their tick. You can use this for non-interactive CPU-intensive background activities that you know has no thing. It's very, very similar to setting the nice level to -19. It's not exactly the same effect, but it's there. That's what it's for. It's part of the POSIX API. The kernel is doing the most sensible thing it can with it, but again, it is difficult to express when you would find a good, there's examples where it would make sense to market a shed batch, but the difference between shed batch and shed other with an appropriate nice level is so difficult to figure out. It's something to note about, but it's not necessarily important to remember that you've got that capability. And then finally, you have shed idle, which is for extremely low priority jobs. Literally, you only end up in these things when you are about to go idle, which gives us an extremely low priority. The nice level has no influence on this particular policy. We're running at an even lower level of CPU under competition than you would get at the +19 nice level. So this one does much more than shed batch makes sense because we can see what it does. It's only going to do stuff when there's no other work to do. And that is what you want to do for something like opportunistic background work, thumbnailing, video stream, trick modes, etc. like that. So shed idle does make sense in the sense it's quite clear what it's for and what it does. The problem with shed batch is not a problem. It's the fact that the actual difference between shed batch and shed other with the same nice levels is so subtle that quite often it's too complicated to figure out which one is best, and you stick to the default. It's actually the best way I can express it. The way the scheduler reacts to losing, it's a tiny piece of code. You can go and find it if you look for it. You just search for shed batch and find the branch missing in the kernel. But the actual kind of mathematical effect of that is much harder to figure out. So that was the completely fair scheduler. We will look a little bit more detail into how that works next week, but for now, that is the default that we use for non-real-time activity. So we come to real-time activity at this point. We come to priority-based scheduling. And this is the real-time scheduling traditionally. So Linux provides two different real-time scheduling policies, shed FIFO and shed RR, which stands for round robin. And first and foremost, a thread that is scheduled using shed FIFO or shed RR will always preempt normal threads running on the same processor. So I mentioned that the effective static priority of everything running shed normal is 0. The priorities that you can choose for shed FIFO and shed RR vary between 1 and 99, where 1 is the lowest. In other words, that is 1 bigger than the 0 priority that all the CFS schedulers have. Real-time scheduling is very, very simple. Basically, the scheduler maintains a list of runnable threads at each priority. And whenever it is called upon to make a scheduling decision, it will look for the non-empty list with the highest static priority, and that is the thread it will select to run. There is no heuristic, there is no completely fair scheduling, there is no sleeper fairness. There is simply, this is the next queued highest priority task. The queues themselves, the lists of runnable tasks, are maintained in the order the task became runnable. So when a task is first made runnable and the list is empty, it's obviously naturally the head of the list. The next one to maintain become runnable is added at the end of the list. So it is the longest waiting of the competing tasks at that priority. The difference between the scheduling classes is pretty subtle. So FIFO, first in, first out scheduling, is essentially a simple scheduler without any form of time slicing. So a sched FIFO task will run until it is either blocked because it makes some kind of sleeping system call, an IO request. It could be preempted by a higher priority thread. It could also call shed yield, which basically takes the task off the CPU and puts it back at the end of the run queue. So shed yield allows you to stop running and allow another task of the same priority to have a little bit of CPU time. But if you call shed yield and you're still the highest priority task in the system and there's nothing else competing with you, you'll remain on the processor. So those are the 3 ways a shed FIFO task can leave the CPU. Shed round robin is basically exactly the same as shed FIFO, except that each thread gets a time quantum. And once that is exceeded, if there is another runnable task at the same priority level, you effectively have the same effect as doing a shed yield. So it's at that point, after you've consumed your time slice, you'll be involuntarily yanked off the CPU, put at the back of the run queue, and anything else in the run queue will be given an opportunity to run. If you're the only thing in the run queue, then that's absolutely fine. You can change the length of the time quantum using the API that we've pulled up there, so you don't have to work on ticks, but it is measured in, it's quantized to ticks. So if you set an interval smaller than you've set config hertz, which defaults to 100 hertz, so if you set it to a 1 millisecond interval, you will only achieve that if you've also modified config hertz to be 1 millisecond. So what might we do to our exemplar real-time system once we have the real-time scheduler? Here's an example, one possibility. There are many different ways you could design it, but in this circumstance, I have set the control loops all to have very high static priorities. Excuse me. Sorry, that was a sneeze that won't happen. So we have very high static priorities on our control loops. We concluded that we did have the separate red button, and while the management of the control surfaces and the stability of whatever it is we're keeping under control is more important than handling the red button. Just to explain that, so if that's a message that you can broadcast to a drone to bring it safely to the ground, for example, that's quite a complicated activity. But more than that, if the control loops aren't serviced, even the emergency beacon saying bring it back down to the ground, you'll lose flight stability before you've reacted. So it's always been more important to manipulate the control surfaces. Similarly, in industrial process, if the control surface maintain the balance of whatever process we're controlling, keeping it in balance is more important than reactions to be red button. And in any case, we expect to be specified that there's plenty of spare capacity to honor the red button as well. So that's why it's slightly lower. And then the control targets, we've kept as a real-time activity, but it's a much lower threshold now. So we have very high priority. This one's debatable. You could argue back and forth about what exactly the right level is for that, but we've put it down a bit. And then we've got a much lower real-time priority on the control surfaces. The local UE, mesh network, HTTP are all using CFS. So the final scheduler that we want to discuss is the deadline scheduler. And the deadline scheduler is very suitable to anything whose it's time-based, as in it's really intuitive to understand it for something that has a period. The controllers in those control loops typically have a period. They have to run, in the example I gave before, is every 10 milliseconds, they have to read the measurables, they have to manipulate the control surface, and then they have to complete that within a certain window, weighted up towards the beginning of that slice of 10 milliseconds. Deadline scheduling is really good at things that you can express in that manner, that within this time frame, you have to have done an action within this sorry, you have to react within a certain period of time, and after a certain period of time has elapsed, you get to do it again. That's what the deadline scheduler is really good at working with. And that one provides us guarantees that we cannot get using the priority system. When a deadline task is accepted by the scheduler, so we can tell the scheduler that we require 1 millisecond every 10 milliseconds guaranteed. If the scheduler allows us to add the task to any run queue, the scheduler is guaranteeing us that that will always be met, that the as fast as specified can be met, and that we don't have to test for it in some sense. Obviously, you have to test to make sure there's no mistakes, but the scheduler is guaranteeing that the system is schedulable, meaning that you can meet the requirements with the weight that you've got on it. Using priority scheduling, it's possible to design systems where in the worst case, we exhaust CPU resource and we cannot meet the deadline under certain circumstances. If we get 5 different things firing at once, the least priority of them may actually miss its real-time deadline. Deadline scaling doesn't have that property because we test before we allow us to run this thing by counting up what resources we've guaranteed to provide. So this is based on a schedule angle called earliest deadline first. So because we know for each task how much time it's going to consume and when its deadline is, we can actually schedule the work not based on priority, but on which task we need to get done first. So we can schedule for the earliest deadline. So there's no effective priority now. Things are only prioritized by how long until it is before their deadline is reached. So to do that, each task has associated with it a budget, which is the amount of CPU it needs to consume to meet its requirements. A period, which is how often we need to run the task, and a deadline, which is the how long it will take us to run it. So previously, I've described to you the period and the deadline. With our control loops, I gave you a 10 millisecond period and a 1 millisecond deadline. What we have to add to do deadline scheduling is a budget. Within that millisecond, how much CPU time will it consume to meet whatever the task is? And it would be quite common for that to be smaller than the deadline. So we might have to take half a millisecond of processing to read all the measurables and modify the control surfaces. And we have to complete that within a 1 millisecond window. So that gives us a budget. That's the amount of CPU time it takes us to satisfy whatever the hardware needs us to satisfy. And once we've done that, the CPU, the scheduler can actually guarantee that we can meet this requirement. We know that there is a deadline. We know that we've got to react to it, and we can check. So if we have if the deadlines are too short, we may not be able to accept other threads, other activity onto the system, because we wouldn't be able to guarantee to meet it under all circumstances. So we can mathematically have entry tests that say, if we've got this, it will fit on the CPU resources we have. It's the budget that makes all this work. So if a task seeks to execute for longer than its budget, it gets throttled. So it's basically saying that that task has misbehaved. That is the task that we punished for misbehaving. That's the one that will lose access to the CPU, so that all the other tasks that have not become broken will continue to work. And hopefully at that point, some kind of quality of service monitor or something will observe that it's happened. It will either kill off, go into emergency mode, limp mode, whatever it is. Once the system has gone wrong, we know which bit's gone wrong, and we have to try and figure out how to fix it. But if we can say within budget, the system is guaranteed to be schedulable. So we can diagram it a bit like this. So once the event comes in, the arrival, wake up time, there's that gap before we do the start time. We have a run time, which is measured from the start time. That's the maximum amount of time we can spend. That's the budget. We have a deadline, which is measured from the arrival to wake up time. That's the time at which the deadline must be met. And we have the period. So for periodic interrupts, things that are happening with fixed time delays, period is very understandable. You can use deadline scheduling for things that we can't predict the time of, but there has to be a minimum gap between activations. So if you have something that runs with an unpredictable time, you do need to be able to express that there is a minimum gap before it can be reasserted. And that's what you would set as the period. So if you can't express a minimum gap between activations, the deadline scheduler actually doesn't work because you can't set an appropriate period. So like I say, for time-based control loops, it's an absolute dead fit. Hence, the kind of most sophisticated view of that example system I showed you at the beginning would be to elevate those control loops to sched deadline, because we can express them as periods, and we can then guarantee that all our control loops can fit on our machine. Compared to the last time you saw this diagram, the ones at the bottom haven't changed. So control is still sched 5040. And the big red button is sched FIFO 80. Incidentally, sorry, I should have mentioned this. Control loops. I've got multiple control loops there. This is the older one where I set this to sched FIFO. Why didn't I use sched RR? Which is a legitimate question. These are multiple control loops, all running at the same priority. They will compete and one can dominate. The reason I didn't use sched RR is because I still have to be able to fit in the worst case activation patterns. All the control loops still have to fit into the available CPU time. Otherwise, I can't meet my real-time goals. Nothing that you do when you add sched RR can make you more likely to meet your goals, assuming that the control loops are not themselves buggy. So because they have orthogonal code, we don't expect one to break and the others to survive. It wouldn't make sense. So the whole time slicing aspect between them doesn't provide anything useful here. We're guaranteed if they all activate in the worst case, I say guaranteed, we have asserted that if they all activate in the same case, there is enough time to complete them before the deadlines, which means that no form of time slicing can help us to meet those deadlines. And since no form of time slicing can actually help us, I adopt sched FIFO. And in general, I'm always a little worried about real-time systems on Linux that have been structured using sched RR, because that usually means that there is some interaction between processes that the designer didn't understand, because they're relying on time slicing to make everything work. So it's a strange tick. If you've had a background in real-time operating systems, particularly ones without very many priorities, you expect time slicing to be there because you usually have a big soup at the bottom of all the tasks running at priority close to 0, of all the things you couldn't figure out how to priority, and you let time slicing do the work. On Linux, you let CFS, the normal scheduler, do that job of trying to figure out how to schedule the soup at the bottom that you can't work out how to prioritize. That means that time slicing is much, much less important on the real-time scheduler sched FIFO than it would be on a classic RTOS, because we don't have that slice at the bottom that we couldn't figure out what to do with, because the slice at the bottom sits on a completely different scheduler anyway. Sorry to jump back to that, but like I said, it's an important point of why I adopted sched FIFO here rather than sched RR, is because adopting sched RR is usually a sign of an underconfident design or an excessive use of real-time priorities. It's not that you can't use it, to be clear, but it's a thing that if you see, you should investigate. Has the designer done this because they couldn't figure out how to prioritize correctly? So quick summary of how to use these different scheduler classes. So ultimately, pthreads API gives us most of what we want here. Pthreads allows us to create threads, and they can be given different scheduling classes to their parents if you would like to. So when you're creating a new pthread, it takes a pthread attra object. And one of the things you can do in that is get or clear inherit sched. So inherit sched says when you create a pthread, copy whatever the scheduler characteristics, real time, not real time, nice level, not nice level, etc. Copy them from my parent. So that's inherit sched, and that's the default. So when you create a pthread attra, the default is inherit sched, and that's one of the reasons why if you set the scheduler policy without reading how the API works, you won't get any real-time behavior because you've adopted this default of inheriting from your parent. Once you've set it to explicit scheduler, you then have to set at least the scheduler policy, sched normal, sched other, sched FIFO, sched deadline. And you can get and set the scheduler parameters to give you things like the static priority and other associated values that you need to make scheduling decisions. And then when you pthread create, you hand that object to the pthread create, and if you have appropriate permissions, classically your root, or you've got capabilities that are inherited from somewhere, then you'll be allowed to create the real-time thread. You can modify the priority of existing pthreads. Most commonly, this will be run on yourself. So you can have pthreads that are spawned off, perhaps do a bit of memory allocation, which generally doesn't want to be real time. And then once they've got all the memory and everything established and they're ready to go, they can change their own scheduling parameters to real time It's the same inherited capabilities or root permissions that you need to take adopt the real-time scheduler, but this allows you to set it on an already existing pthread. You can reach across and set other pthreads real-time. I struggle to find a use for that. If it appears in your design, that's great. But yes, I can see why you would choose to call this API on yourself after you have established certain operating criteria. And then finally, there is a Unix API, meaning one old school Unix API that does not use pthreads, that can operate on process identifiers, PIDs. So this allows you to reach across and set another process to be real time. Basically, this comes up because not all Unix processes use pthreads. Some of them only contain one thread, they only do one thing, hopefully they do it well. And on some occasions, you might want to bump up that single threaded component to a different priority. This is particularly important if you ever have to get into tuning K threads. So K threads are kernel threads. They exist for dispatching work queues, for handling various types of soft and hard interrupts in the real-time systems. So you have threads inside the kernel, threaded interrupt handlers, for example. If you are working on highly tuned systems, you might actually need to reach in and change the scheduler characteristics to K threads. You can't use the pthread API, obviously, because they're not pthreads, but they do have a PID, just like any other schedulable execution context. So one of the best uses for shared set scheduler is to reach in and tune K threads. Now, next week, I'm going to say only tune K threads if you have to, but sometimes you do have to. So this is a good API for doing that. And then finally, you can do a lot of this at the command line if you want to. So you can actually just kick off tasks with particular activities. So CHRT, command line tool, it can manipulate schedule policy as it creates subprocesses. So we have an example here where RT job is a shell, a set of arguments and the executable name. And we're just prefixing RT job with CHRT, FIFO scheduler. You have to be careful with minus PID. I beg your pardon, sorry, this is an existing thread, yes. So the command processor here, this is not saying target PID 50. I've put it in this order because it's a little bit awkward. FIFO does what it obviously says, shed FIFO. Minus PID says, I want to change an existing thread. I don't want to kick off a new process. But then the argument after it is actually priority that we're going to apply to something, the static priority. And then finally, we have, in this case, RT job. It doesn't contain an executable at all. Sorry, it contains a PID. So this is not saying go to PID 50 and adjust something. It's saying go to PID RT job and set the priority to 50. Once you understand that, the syntax to change the scheduler parameters to non-real time start to make sense. So here we're saying I would like to change all threads within this process. So it's not just targeting a specific PID, but it's targeting all its children. I want to set it to batch scheduling, and I'm going to do it by PID. I then have to set the static priority to 0 because all shared normal activity has a static priority of 0, and then I set the PID. So CHRT does have this quirky behavior that it always takes 2 arguments if you put it into PID mode. And it does make it quite hard to read because you say minus PID and the thing that follows it is not a PID. It's the second one that is actually the PID. That's its life, that's what it does. And I think the reason it does it, you can see at the bottom here. So this is kicking off a background activity. It's doing a background transcode. So it's asked for idle priority with a static priority of 0, and then it is running these creating a transcode process with those arguments. And here, this is the same 0, the same 0, the same 50. So always the first argument to CHRT is the static priority, regardless of whether you're in PID mode or in command line mode. So it's quirky, but it is a useful way to launch real-time activity from the command line. And then finally, we should talk about the user space API for the deadline class. So Shed set Atra is part of the upstream kernel, and it provides the means to configure deadline scheduling. Unfortunately, the deadline scheduler requires additional arguments, runtime, deadline, and period, that are not provided for under the original POSIX API that glibc implemented, and it was not possible to add it in a backwards compatible way. So some of the APIs I showed you before can't meaningfully set the scheduling class to schedDeadline because they only contain these scheduling attributes. They're not able to set a runtime, a deadline, and a period. So there are two different ways you can set up deadline scheduler if you want to. The first is basically to include kernel headers directly. These structures that I'm showing you here and the number of the system call and everything else all come from the kernel headers. And then you can write your own version of sed_set_attra that just makes a system call to shed_set_attra, which you can look up in the man pages for, and it allows you to set the additional deadline modes. If you're writing open source GPL code, you can also use a library available for it as part of this set of tools here. You can also have a glance at that to understand how it works in a bit more depth if you want to understand more about the example on the screen. We just check how, yeah, where we're going to, okay. Last awkward property of real-time processing is, I mentioned that shed_FIFO, shed_RR, you tend to prefer shed_FIFO because shed_RR implies that you're relying on time slicing for your system's correctness, and that's not always a good idea. There is a slightly more significant concern, and that's if a real-time process becomes, it stops working correctly and starts to consume CPU indefinitely, infinite loop, just doing, not being able to meet its deadline and running continuously, whatever it is. That will make the system almost impossible to debug. And the reason that will happen is because your shell that runs your serial port are all running on the normal scheduler, which has a static priority of 0. And although you can have JTAG debuggers and other external mechanisms to debug Linux systems, the vast majority of stuff that the vast majority of tools that you have to work with user space to make sure user space is working correctly run on the target itself. If I have a badly behaved real-time process, the thing I'd really like to do is to attach a debugger and stop it running so I can find out what loop it's stuck in. For example, if it is running and dominating the CPU, I can't start the debugger. If it's running a debugger, I can't even have the debugger react properly to signals because it won't get any scheduling time. If it's running a GDB server, it can't even receive the request from the remote end to say stop a task because the real-time task is dominating the CPU and it's not giving anybody else a chance. So to counter this, one technique that is often used is a simple ceiling on the amount of time you can spend in the real-time scheduler. And it's effectively a throttle. So if all the real-time tasks combined together consume more than a specific amount of runtime, they will be stopped. And they will be stopped for a short window to allow non-real-time tasks to run almost exclusively for the purposes of debugging. So if your real-time tasks go rogue and you're unable to interact with the system, it will reserve just enough CPU time for you to fire the debugger, to kill the process, whatever it is you need to do to understand what's happened, even to run top and see, oh, it's that one that's gone wrong. Right? It's that kind of level of debug. None of that is possible if your real-time tasks are consuming 100% of the CPU. So there is this inheritable R limit, a ceiling on CPU time that can be used. That basically says that if something goes rogue, then after it's consumed too much CPU time, we'll kill it. The other one is these proc files, which allow us to set a period and a runtime. So this allows us to say that I could set this to say 100 milliseconds. This can be quite a human scale. I can set to say 100 milliseconds. And I can say within those 100 milliseconds, you may not spend more than 95% of the time. So this would be 95 milliseconds. You may not spend more than 95% of the time running real-time activities. That'd be quite lumpy. That would mean every 10th of a second, we'd get a tiny slice of runtime, which would feel lumpy to type into. It wouldn't be great. It would feel lumpy to type into. So I've just pressed a button that takes my slideshow out of slideshow mode. So it'd feel lumpy to type into, but you would be able to run just enough to figure out what's going on and at least either find the rogue process and kill it, or find the rogue process and attach a debugger to it so that you can find out what loop it's stuck in. Or if it was a real-time process that's going to do damage, you can reboot as fast as possible. I mean, it can simply be a, oh, we've reached this situation, reboot. I mean, if you're not debugging, you just want to have a system that's a bit more resilient, you can say, out of spec, we know something's gone wrong, kill. But that's the techniques we can use to do that. So, do we work this in for 2 hours, I think? I think I'm going to run straight through. So I'm going to move on to the other parts of this. I particularly want to get down and have enough time to do memory management, because that's some of the hardest bits to understand and some of the deepest parts of the user space that we need to think about. But I will talk briefly about pthread mutexes. So pthread mutexes are mutexes. There's an API on the screen. Their job is to create a critical section. You lock them, you do something, you unlock them. That's what a mutex does. It's well understood. I hope if you're building real-time systems that you are able to work with mutexes effectively. They allow us to have concurrent access from multiple places. What is less well known about pthread mutexes is they implement, again, protocols. Similar to the scheduler, you can actually ask mutexes to behave in different ways by adopting different protocols. The default protocol is none. You saw in the last one we created this mutex with pthread mutex initializer. That will have initialized mutex with a non-protocol, no priority protocol, which means you adopt the fastest and most efficient mutex, but also the least fair, or at least the one that does not respect processing priority. And why might we care about that? Well, I have to tell you what priority inversion is. So priority inversion effectively happens when a lower priority task is preventing a higher priority task from completing its job. And it occurs when mutexes are shared between different priorities. So we've diagrammed it like this. We have increasing priority up the top. So thread A is the least priority thread in the system. Thread B is the most priority thread in the system. And then we've got thread C, which sits at an intermediate level between them. And we have an activity schedule like this. So thread A has acquired a lock, which is fine. It's allowed to take a lock. It's doing some work. However, before it's managed to release the lock, it was preempted by thread B. Thread B then did some work and attempted to take the same lock. So it blocks and waits for thread A to release the lock. That's what locks are for, which is all very lovely, except unfortunately, thread A was preempted by thread C. So at this point, the right thing is happening. Thread A is preventing thread B from running, but this isn't priority inversion because it is inside the critical section that thread B wants to enter. Priority inversion happens when something that is uninvolved in the lock interrupts thread A. So at this point, the most important thing the system has to do to allow thread B to run is to let thread A have CPU time so that it can release the lock. And at that point, thread B will naturally preempt thread C and will take priority. But unfortunately, because we are not using a priority protocol on our mutex, then when we take the lock on thread A, then thread C is now, the system is no longer running the thing that is most important to allowing thread B to progress. This is called priority inversion. It's quite famous. If you type Mars rover priority inversion, you will discover how the Mars rover had an intermediate thread that caused it to work incorrectly when on the surface of Mars, which was highly inconvenient to all the scientists involved in the program. And I believe it had a happy ending because I believe they were able to remotely firmware update it to add a priority protocol to those mutexes. But it's a long time since I read it, but it's worth a read, and it's a classic description of what can go wrong if you have priority inversion. It's not purely theoretic. What happens when you have priority inheritance? So this is a different mutex priority protocol that allows us to avoid these problems. So we have the same beginning. So we've got as far as thread B. But what happens when thread B attempts to take a lock that thread A owns is thread A will temporarily inherit the priority of thread B. So if you remember, thread C became runnable about here. But because thread A has inherited the priority of thread B, thread A now gets to keep the CPU. Because when thread A holds a lock that thread B wants, the most important thing to do is to run thread A until it releases the lock. When it releases the lock, thread A will immediately drop its priority back to its original value down here. And that means that thread B will immediately preempt it at the moment it releases the lock. It will acquire the lock, it will do the work, it will release things. Priority inheritance is a particularly tricky thing in some sense, because if you have implemented a logging infrastructure in your app, you probably have a lock to prevent different threads from logging at the same time to create awkward output, difficult interleavings. What that means basically is the debug mechanism is one of the most likely places that you've got where you've got a mutex that's shared between lots of threads and is actually the mechanism by which you can produce priority inheritance problems. So that's one of the reasons we want to introduce you to this idea of priority inheritance, particularly whenever you're sharing locks between multiple threads of different priorities. You have to take account of whether there are intermediate priority threads that can cause real-time hazards. Because ultimately what would have happened in the previous slide here is eventually thread B would likely miss its deadline because thread C has taken what it needed. There is a simpler protocol. So I've implemented priority inheritance back in the day on an old school RTOS, and it is an ON thing because you have to track through all the different owners of locks. It can be surprisingly complicated as locks interact, trying to figure out whose task you inherit the priority from and how you unwind it again. So it's quite a complicated piece of code. It's standard bit of operating system code, but it does involve a certain amount of management and overhead. So there is a simpler, cheaper, faster way to achieve essentially the same goal. And that is by using something called priority protect or priority sealing. And that's quite simple. You don't just have priorities associated with locks. You also associate, priorities associated with threads. You also actually associate a specific priority with a lock, such that lock ownership elevates your priority automatically. So in other words, I don't know if we diagrammed this actually, we should have done. At the point thread A acquires the lock, it will actually immediately start running at the priority sealing value. And so thread B wouldn't run until thread A unlocks the sealing mutex, and then thread B would run. So it doesn't produce the same thread schedule as priority inheritance, because owning the lock unconditionally boosts the priority of the thread so that it's able to release it ready to give it to somebody else. This does create its own subtle inversions, which is while you own the lock, thread A might not be contending with thread B, and therefore you should let thread C run. You should, inheritance only boosts the priority when there is contention on the lock. Priority protect always boosts the priority. It's much cheaper, which is why it exists. There's no recursive tracking, but it creates an opposite problem, which is when you're locking, you end up with an excessive priority potentially. Which is fine if you've got short period locks. If you've got locks that come up, you do a small amount of work in a critical section and release it. Yeah, theoretically, it's not the ideal thread schedule, but because you're only locking for a small period of time, you don't get any significant problems as a result. So that's what this one's for. It solves the same problem effectively, but it's slightly more fragile. Priority inheritance automatically tunes based on changing of thread priorities. If you're using something like priority protect and you change the priority of different threads, you have to go and review all the priority protections to make sure that you've got the levels correct for all the threads that could contend with it. So priority protect definitely has higher maintenance costs, but lower runtime costs. I suppose the best advice is if you're concerned, you should always use inherit unless your profiler tells you there's a reason not to. And one last thing about priority sealing protocol. be very careful reading some of the old literature about priority ceiling protocol. Priority ceiling protocol reads, if you study it, very similar to prior protect, but they're not actually equivalent terms. And some of the really old RTOS literature talks about using PCP to mitigate deadly embrace deadlocks. Because they boost priority, you can get deadly embrace where you take locks in different orders. It doesn't mitigate deadly embrace. It was always a fragile and broken concept, and it simply doesn't work on SMP systems. So some of that literature that you read about PCP is really very old and did not take into account the possibility of SMP systems. So Protect is useful for boosting. It has no benefit in terms of deadly embraces. So if you go back and read old real-time literature, can be very interesting because that's where all the theory was being developed, even to things like deadline. But like I say, some of the summaries, particularly in the books rather than the papers, didn't take account of things like SMP. Okay, so I'm going to very briefly talk about condition variables. And this is probably the biggest departure from real-time. This is just POSIX API. But if you have, it's for the benefit of people who've come from RTOSes and are accustomed to calling interrupt lock. Because one of the fundamental things about Linux is you cannot call interrupt lock. You cannot prevent interrupts from firing from user space. And that means that some of the techniques that you'd use in an RTOS to implement real-time primitives and things like that become unavailable to us. So I've just lost the light that gives me a front light. There we go. So condition variables are an alternative. Not alternative. Yeah, they are. They provide some of the features that an RTOS might implement with interrupt locking. They are not equivalent in any sense. They simply provide features that could not otherwise be implemented. And that is to allow user-authored queuing. So essentially, you can have code that waits for a condition to become true. And whenever a condition changes, you can ping the condition variable and wake up anything that's sleeping on it. And it's a hybrid of conditional variables and mutexes. You'll notice that the conditional variable wait doesn't just take the conditional variable, it also takes a mutex as an argument. And that's to allow us to have correct locking to the point we go to sleep, and so on and so forth, which I'll try and explain. So we have thread B that has locked a mutex, checked a condition, and it's not met. So thread B has decided it needs to sleep until the condition becomes true. So having checked the condition, it calls pthread cond wait, and inside pthread cond wait, it unlocks the mutex. And that means to the point it went to sleep, it knows that the condition has not changed because it owned the mutex by which the shared variable that the condition is held in can be modified. So that's why we have the mutex around it, is to make sure we don't get this in the wrong. You could have a thread schedule where you check the condition, you update the condition, and then you wait, and they'll be stuck waiting for an event that's not going to happen. So we have to use mutexes to allow us to check the condition and make sure that the condition cannot be updated until the point we've actually gone to sleep. That implies you have an opposite process in thread A. Thread A is going to try and wake it up because the condition has changed. Excuse me. Sorry, I'm working with a trackpad. If I touch it incorrectly, it advances the slide. Thread A, lock mutex, update condition. Once the condition has been updated, it can signal the thread, which may wake up simultaneously on another SMP core. It may preempt us even. But what it will do before it does anything else is reacquire the mutex that it gave up when it went to sleep. So it's a single call that guarantees that when you resume, we own the mutex again, ready to run in a loop. Essentially, we can now go and check the condition, and if the condition is met, we can continue. If the condition is not met, we can't. This can, for instance, be used to implement something like a message queue. So thread B in its check condition could be checking for message queue not empty, and if it is empty, it sleeps, and if it's not empty, it will continue. And likewise, this can be the process of enqueuing something to the message queue. So update condition here is writing a message in and then changing the counter to say how many messages are in the queue, and then signaling to wake up anybody who's waiting on the message queue. That's the sort of thing you can build with condition variables. Sorry, excuse me. Okay, so condition variables. There are some other useful APIs involved in it. We've only shown you the concept because it's literally, I just wanted to help people with a real RTOS background recognize that there are techniques you can use to avoid interblocking. Because equally, you can implement some of this in interblocks, providing interblocks are dropped when you deschedule. You can do the same sort of trick with interblocks. So the other useful APIs, we've got APIs to initialize them. Broadcast allows us to signal all threads. So occasionally you want multiple threads to wait till the same things happened. So we can wait all threads that are waiting for a condition if we want to with a broadcast. Timed wait is equivalent to wait, but allows you to block until a particular point is reached in time. And then we've got cleanup as well. So that's just some APIs to follow these things. So conditional variables allow us to notify tasks that particular conditions have been met. When you initialize them, you can set them to be shared. That is very, very rare because that would imply you've set up multiple processes that have been configured in such a way as to share memory, which is quite unusual. It can crop up in message passing systems, but most of the time you create a single process containing multiple threads, all in one memory space, and so you don't need to set the shared feature. That's it on condition variables. Like I say, I just wanted to introduce people to that kind of API. So similarly, we need to talk similarly briefly, I guess, about signals, because they have many properties in common with interrupts, and they do have impact on real time. So signals are ultimately a form of interprocess communication, but they're a very idiosyncratic one. They're a synchronous notification event, and critically, they can occur at any time. And they're delivered to a particular process, which is a group of threads. So they can occur at any time. That does include when you're executing system calls. And typically, if you get a signal raised during a sleeping system call, and indeed some non-sleeping ones, then that system call will abort, return control to the user space, where the user space will jump to a specific handler to act on receiving the signal. Signals are maskable, so you can prevent this by masking signals. But essentially, when a process receives a signal, one of the threads where it's not masked will stop its normal execution and jump to the signal handler. You don't get to choose which thread it is, except by the mask. In other words, if you receive a signal, it could be dumped directly into your real-time task, and your real-time task might be diverted from doing its work by receipt of the signal. It's why we want to talk about signals. They're not free. They are run in normal user execution context. Basically, it just reaches in and fudges the PC so that you jump into the handler instead. And yes, if you don't take account of them, they can be delivered to your real-time process and completely mess things up. So some examples of signals that you get. I mean, Control-C is probably the signal which you are most familiar with, even if you aren't really thinking about how it works. So Control-C interacts with the terminal subsystem and generates a signal on the foreground process running within that terminal. The other thing that you commonly see them for is things like invalid memory access. That when you do an invalid memory access, a signal is actually delivered to a process to give the process a chance to recover if it wants to, but the default handler for both Control-C and invalid memory access is to kill the process. There are other signals that can happen. You can have alarms. You can say, signal me in 3 seconds, and 3 seconds later, a signal will be delivered to your process. And another subtle one that comes up from time to time is the reread of config file. So when you've got a background daemon and you've gone into etc. and changed its config file, in a lot of cases, when you do the system cuttle restart, what's actually happening is a signal is being delivered to the daemon to ask it to go and reread its config files. It's not always the case. Sometimes they kill the daemons and restart them, but quite often when you ask a daemon to restart, all you've actually done is send it a signal to ask it to reread its config file. Those are just common examples. Signals have lots and lots of other uses and applications, but those are the ones that you're most likely to be familiar with. Signals do travel through the kernel, and some can actually be created within the kernel, and some are handled by the kernel. So we'll start with most signals. Most signals are generated by let's be clear about this. This is most signals by the configuration space. So there are 30 something signals, I think, 66. So there are many signals, and by number, most of them are not special. Most of them are raised by one process. They are sent to another process, and the kernel mediates it. So that when you raise a process, you know, that sig user that causes a reread of config file, a process raises it, and another process handles it. There are a couple of signals that do not get sent to the process. So sig kill and sig stop. Sig kill completely destroys a process. Sig stop is a debugging mechanism. They're handled by the kernel. So if you send a process and ask to kill another process or stop another process, the kernel handles that for you. The process 2 is never involved. There are also signals that can be generated by the kernel itself. Segmentation fault, sigint, sigchild can all be generated by the kernel and delivered to a process without some other process having sent them first. And for the thread that receives the signal, it basically looks like we're doing some work, and the signal is delivered. And what happens when the signal is delivered is literally a new stack frame is created. The program counter is shifted over to somewhere entirely new, and it's arranged that when you return from the signal handler, you'll end up back running the original code with the original register set without the original code being able to recognize that the signal handler's ever happened. So we can run the signal handler, and the signal handler will either react to the signal and do some work, or it might, if it's the defaults, it might try and kill the process or something like that. You'll notice here there's no locking. So the set of APIs you can use from within your signal handler is heavily restricted, because you cannot do anything that might interfere with the underlying process state, like, for example, allocate memory, because you would then have a lock that is needed here to run in malloc and a lock that's needed here to enter malloc, and you deadlock. So the set of APIs you can use within your signal handler is extremely narrow. We've got a list of common signals. Like I say, we've highlighted sigint for you. And we've got some default actions as well. Did we summarize them? Yeah. So T stands for terminate. So many of the signals default to terminate. If you have not caught the signal within your process, many processes will cause a termination. You can also have abnormal termination, which is where you get a terminate at core dump. You can ignore by default. But that's just a list of some useful signals. Signals are a pain because of the interrupty sort of nature to them, and the fact they can be delivered to arbitrary, they can sort of steal processing time from arbitrary threads. They are awkward to deal with. They are difficult to reason about in the real-time perspective, and I generally try to avoid using signals when I have the option. Just because I find other techniques easier to reason about. There are even things called real-time signals, which act much like old school signals do, but with a few, it's less broken, but it's still awkward and slightly difficult to use. So the key thing they've introduced, is a number of new signals, numbers, and also a queuing mechanism. So a traditional signal is a flag. It gets raised and it gets lowered when you've completed the signal handler, which means if you get two signals delivered to a process, you can't tell. A process simply cannot tell if it's ever received two signals or one signal. Real-time signals are counted. So you get as many signals as were sent. And there's also a mechanism to provide a little bit of additional information alongside the signal. So these get used for things like POSIX timers, POSIX message queues, and can be used for asynchronous I/O. They do have a good set of values. You know, they are useful for application programming, but despite the name, I'm still personally not very keen on them for real-time systems. The problem here is that real-time means the passage of a clock that is working in real time. A second is a second long. Whereas working in batch mode, you might be processing a second worth of video in a quarter of a second. You are not working in real time. There is no external measurement of time involved. For a timer expiry, that is measuring real time. For asynchronous I/O operations in big systems, you need to count them, you need to handle them correctly. So I don't want to say don't use these things. It's not as absolute as that. But signaling will make your design much more complicated. And you will have to take steps to make sure that the signals are delivered to the correct thread within your process that is the right priority to broke or whatever it is that's happening. So in initial designs, like I say, I prefer not to work with them. We haven't actually talked about masking. So you can mask signals. So one common design that you get in multi-threaded applications is signals are masked throughout the application. Signals are fully masked, but a single process can actually poll and say, are there any flags set? Please wake me up when there's light. And you actually create a thread whose sole purpose is to wait for fixed signals and handle them. And that effectively converts the reasoning for signals from being a complex, where is it going to get delivered? What's it going to do to my timings? What's it going to mess things up? To having a single thread whose sole, single and unique purpose is to handle signals. That makes it much easier to reason about, but quite often the preemptive nature of signals then doesn't work and you don't get the benefit. So if you come up with a good real-time design with signals, great, but don't think you have to integrate them unless you need them, because if you can avoid them, your life is going to be simpler and easier. And then finally, before we get to that tricky memory management section, I want to talk about clocks and timers. So here again, we have that concept of the real-time clock. This is a clock that measures real time. In this case, real time means calendar time. And calendars do some very freaky things. They have leap seconds. They jump backwards and forwards randomly by an hour when you go into and out of summertime. And the algorithm for figuring out when you go into in and out of summertime is under the whim and control of governments, who sometimes tweak them. And then there's a big database to tell things when they go in and out of particular time zones. And in the case of laptops and other mobile devices, time also changes when you fly around the world and you move it to a different time zone. So clock real time measures calendar time. Calendar time is useful if you want to wake up at a particular point in the calendar. It is not useful if you want to wake up 10 milliseconds in the future, because you tell it to wake up 10 milliseconds in the future. You then set the clock back an hour because you've changed to a different summertime, wintertime. And then it's actually an hour and 10 milliseconds before you ever wake up. So clock real time is really ideally only used for calendar time. If you want to use relative time, I want to wake up 10 milliseconds from now. The clock that you almost always want to reach towards is called clock monotonic. Clock monotonic monotonically increases. It never goes backwards. It's called monotonic rather than constant, because constant involves some difficult theory about temperature drifting, crystals, and heaven knows what. To all intents and purposes, it's the best time that we have on the device. So clock monotonic is going to be counting fairly accurately, and it always increases. So when you set it 10 milliseconds in the future and you're measuring against clock monotonic, it will happen 10 milliseconds in the future. The other thing that is important about time, particularly if you're working on a thread that periodically wakes up, is that you should use absolute time values for periodic wake-ups. This is kind of real-time programming 101. But if you have sleep 10 milliseconds, do something, sleep 10 milliseconds, then you will always take slightly more than 10 milliseconds to do the work, and you'll slowly drift as you have different latencies to rearm the timer. So if you want something to happen every 10 milliseconds, you use an absolute wake-up time. You then take the old wake-up time, add 10 to it, and set that as the new absolute wake-up time, and then you get wake-ups without drift. There are other clocks within the system. for specialized use cases. So we have some things that measure the consumption of CPU time. We have clock boot time, which is essentially the same as clock monotonic, but it continues to count when the system is suspended. So this does occasionally crop up in real-time systems. If it's something like a weather station that wakes up every hour to read a measurement and send it to another node via a mesh network back to, so to have a distributed weather system, weather measurement system, then the system will actually spend most of its time suspended for battery reasons. And those ones you would want to measure wake ups using clock boot time to make sure that you are actually programming a wake up. So I beg you, actually need to measure against boot time alarm, sorry, because that will also do the wake up when you reach it. So you can measure from boot time. You can also measure from boot time and arrange that if you've got a wake up, that you're waking up with it as well. So these two can be used to wake up at specific calendar times or specific relative offsets. There are also a few funkier ones. You can have versions of clock monotonic that does not account for crystal drift. So normally clock monotonic, if you've got something like network time protocol running, will actually figure out over time the difference between the actual passage of time on the atomic clocks that drive NTP and the drift on your local crystal because of its error. And it will account for that, and clock monotonic will give you the best clock you've got. So if you've got network time, it will give you the best clock there is. Occasionally, you actually want to measure time against the crystal. For example, if the crystal is feeding the VSync machinery, you want to measure time using the same crystal, otherwise you'll start drifting against the audio video against the VSync machinery. So there are occasional mechanisms where you have that. There are also a couple of faster clocks like clock monotonic course, which for ARM V8 systems is irrelevant because clock monotonic is very, very fast and highly optimized. But on some systems with more complex clock architectures, clock monotonic course can give you faster access to a lower resolution clock. So you can read the man pages to learn more about the different types of clocks, but the key message is this is the one that you use unless you've got a reason to pick something else. So you use clock real time if it's calendar, use clock monotonic for everything else, unless there is a really strong reason that you have to pick something else. Clock access APIs, I'm actually going to speed through these. You can read clocks, would you believe it? You can find out what their value is in seconds and nanoseconds since some epoch. Clock monotonic tends to epoch at power on time. Obviously, clock real time uses the famous 1970 epoch, and all the other relative clocks tend to be reference and power on. You can find the resolution of the clock, and if it's a settable clock, a calendar time clock, you can set it as well. There are APIs for precise sleeping. So if you man sleep, for example, it will give you a resolution in seconds. Seconds are all very well, but they're not necessarily what you want for short sleeps. So we have nanosleep, which is a simple high resolution sleep of this is a relative sleep. I mentioned that we want to do absolute sleep most of the time. So nanosleep can be a high resolution sleep. It measures the interval with clock monotonic, but it's a relative sleep. So it takes the time now, adds requests to it, and that's the time that you sleep for. Clock monotonic is more, nanosleep is more flexible. It's the same high resolution thing, but you can choose which clock you choose. Again, clock monotonic is a sensible default, and you can set an absolute wake up time, which means you can set your loop to every 10 milliseconds, wake up, do something, go back to sleep. It's very good for things like control loops. It makes a lot of sense for control loops. There are other system calls that can have similar properties to nanosleep and clock nanosleep. Things like poll and select also perform precise sleeping while also waiting for data to come in. So if you're waiting for an event and then you've got a background activity, poll and select are good for that. So there are options, but clock and nanosleep, if you just want to sleep for a particular period, those are the APIs to look for. And finally, we have these signal-based alarms and interval timers, which, like I say, I would, depending on, it does depend on how many timers you've got and what you're trying to do. There's a lot to be said for firing a thread and letting it sleep, if you understand how these things work. But you can set interval timers to do things like reduce stack usage, or because it's a more natural thing for your specific design. So the classic old Unix tools are called alarm and set itimer. Alarm sets a time in seconds to wake up, and it will send you a SIG alarm after those seconds have elapsed. Set iTimer gives you, sorry, let's look at this. So, I got it. So alarm gives you a countdown in seconds. Set iTimer using iTime real gives you the same countdown, but it's measured in microseconds. And in both cases, it will give you a SIG alarm when it expires. Set iTimer also has other options. You can pick iTime real. You can also pick iTime virtual and iTime prof for profiling. These are very useful things. They allow you to measure how much time the processor has used in the process. So you can compare the wall clock to the amount of time you spend. You can say, I've been on the CPU this % of the time. So it's useful for measurement, profiling, self-benchmarking, and things like that. It doesn't have any obvious applications to build a real-time system with. It's a debugging mechanism to measure execution time. If you were trying to figure out how good or bad you are compared to your shed deadline schedule, you want to understand if you're a bit on the wire with your estimation of compute time, you could use this kind of mechanism to count the time that you're spending and make sure you don't use more than you expected. But in general, yeah, they can be used for performance monitoring, but they're not a natural part of a real-time system because they don't measure real time. We have some APIs. I will leave you to read those APIs at your leisure. And then finally, when we get into timers, we also have POSIX timers, which are dramatically improved interval timer API. So the manners in which these are improved is they have nanosecond precision rather than microsecond precision. You have the full choice of clocks, so you can target clock monotonic, clock boot time, whatever you need, and you can have absolute wake-up times, which are useful for starting them running. If you're setting up an interval timer, it will keep ticking at a fixed rate, that's guaranteed, but you might want to position the timing of the first interval. Absolute wake-up time allows you to do that. Just a quick warning about POSIX timers, because they have this beguiling feature called SIG-EV thread, which if you've been listening to what I've been saying about signals, you think, oh, right, excellent. Well, I won't have a timer that sends me a signal. I'll have a timer that wakes up a thread when something goes wrong. So there are 3 wake-up models. There is don't wake me up when the timer expires. This means that you can use get time to observe the timer, and you can figure out where you are in a period or whatever else. So this can be useful if you want to observe time, but you don't get wake-ups. You have the traditional signal-based wake-up that it will send you a signal whenever the timer expires. And you have SIG-EV thread, which will wake up a thread as if, sorry, it wakes up a it calls a function as if it was a start function of a new thread. And you can then set the scheduling priorities of the thread. You can arrange for the thread to come up like a pthread with a particular set of attributes. That would be great. That would be a function that gets called with a particular static priority every time the timer expires. Unfortunately, the language from the spec says we'll call the start function as if it was a new thread. And that's what glibc actually does. It has a non-real-time broker thread that receives the signal, and then it will create a new thread, and then it will call the entry function. So even if the thread that you are creating is a real-time thread, it gets brokered through a non-real-time brokering thread, and any real-time benefit that you might have from using that thread mechanism doesn't happen. So it's a real trap. It's a real trap because the API makes it look like you've got all the real-time properties you'd like and no problems managing your signals. There are other ways C libraries could implement it. I haven't studied Bionic. I haven't studied Muscle to find out if they work the same way. glibc is not uncompliant, and what it's doing makes sense if you're using POSIX timers in non-real-time systems. So bear in mind, POSIX timers are not exclusively for real-time. So glibc is not indefensibly wrong or anything like that, but it's a real trap for real-time systems. If you think that the thread that you're going to be creating is going to be woken up at particular real-time priorities, that is not going to happen. Okay, so that moves us into memory management. And memory management, like I say, is part of the deepest aspect of doing real-time programming on Linux, because of the additional complexities introduced by having virtual memory. So all real-time programmers, if they've got an RTOS background, should be knowing that things like malloc are not deterministic. If you are calling malloc once you have become real-time, it's almost impossible for you to say that you meet the spec, because you have absolutely no idea how long it's going to take malloc to walk through the free memory lists, coping with fragmentation, anything else, possibly making system calls in order to increase the heap size and so on and so forth. There's almost no way, once you've called into malloc, that you can have some idea of how long it's going to take before you get the CPU back. So all real-time applications should be expecting to pre-allocate memory. Either statically, so there's a couple of ways that are commonly done. First, you can simply statically allocate memory. You can either have it on the stack, you can have it as global data, or you could do a big malloc at the beginning and allocate a data structure. The other approach occasionally comes up is pre-allocated memory pools. So if you know, networking is an example that's come up in, you know that you've got the maximum transmittable unit. So you have a pool of pre-allocated networking buffers that you can reach from and grab every time a packet comes in. Now, networking in Linux is as fast as possible, not as fast as specified. So those pre-allocated memory pools are an optimization, and if the pool exhausts, it will actually reach out to a regular allocator and fetch new buffers. But you can have the same principles in real-time systems. You can pre-allocate something based on the maximum possible size that this lump is going to need to be, and you can create an allocator that's much simpler than the malloc, and you simply say, give me a block, it gives you a block, and you've designed the system such that the block pool will never exhaust. All of that remains true on Linux systems. So everything I've said there is true for any real-time system, whether it's implemented on Linux or an RTOS or anything else. You don't generally use heap allocations in critical paths. Paged memory operating systems like Linux, things with virtual memory, all the above is necessary, but it's no longer sufficient to ensure a predictable execution time. And that's because paging adds essentially unbounded or very difficult to measure latencies into real-time programs. So we have our virtual address space. It's divided into fixed size units, pages. Processors occupy a number of pages. They will consist of executable pages, where it gets the code from. It will consist of read-only pages, which is constant data. It will consist of it's quite often called anonymous pages. These are read-write blocks unique to the process, the memory of the process in most cases. There are other places you can get memory from. You can mmap files and so on and so forth. But those three, executable, read-only data, and modifiable data, are the ones that we'll contemplate here. So when you create a process, a new process, what will actually be in memory? Well, very, very little. It will allocate a stack, it will allocate a heap, it will allocate address space to store the code. None of it will be loaded at that point. What will happen is when you start to write to a new block or read to a new block from a new block, that's the point at which it will fetch the resource from the underlying, from where it came from. So when you execute a instruction, that will cause a page fault because we haven't yet loaded the code. We'll then reach out to the disk, we'll fetch the page containing the code, and then we will run it. The same is true with read-only data. The same is even true of the stack. So Linux processes typically have a megabyte of stack. And none of that gets allocated. There's no memory associated with using it until the stack starts to grow downwards. The first time you, and the pages are zero pages, so when you read them, you'll get back zeros. If you attempt to write to one, then a page fault happens. The operating system will go actually and find a page, allocate a page, give the page back to the task, and then allow the write to complete. That's what virtual memory is. Effectively, it's a lazy form of allocation where allocation doesn't actually happen until the page is used. This is a desirable thing. I mean, Linux normally implements a thing called memory overcommit, where it actually allocates more memory than exists within the system. if you sum up the sort of hundreds of threads that you're normally using, my system typically would have a couple of hundred threads by default. Most of those have a megabyte of stack because that's the default. It hasn't allocated 256 megabytes of stack though. It's only allocated pieces of stack that have been used. And that scales up through heap and everything else. And eventually you end up with 200 processes that collectively have got address spaces that are bigger than the physical RAM in a system. And that's useful because it allows to fit more processes in. It's also why the killer exists. So yes, executable code is fetched from disk when you execute it. Unused error paths, C++ unwind tables are never loaded until you hit that error path, which means that the unusual path in your real-time thread isn't in memory until you hit the error. That means there is unbounded delay until you hit the error path. Read-only pages can also be discarded at any time. If you come under memory pressure, the kernel has a choice. It can either take read-write memory and write it out to the swap file, or it can throw away read-only pages because it knows how to get those back from disk already. So the code of your application, the error tables, anything that's read-only, can be discarded from physical memory at any time without reason, because the kernel knows it can refetch it from disk. And like I said, the same is true for read-write pages. This is quite exciting, and it has a number of consequences. First and foremost, it's very, very common for embedded systems to have no swap partition, in the belief that they don't want swap because it'll make things go slow because you have to store the read-write pages and it'll make their real-time systems not work, which is true to a degree. But what you do if you have no swap partition, if you have no swap partition, the kernel has no choice, if it comes under memory pressure, but to discard read-only pages, which typically means code. If you have no swap space, swapping will still happen, or something like swapping will happen, paging will still happen. What will happen is it will page out executable code, and then next time you execute it, there's a big delay while it refetches the executable code from disk. It also means that the fact that freshly allocated process memory doesn't actually have any RAM behind it, unexpected latencies will appear whenever you touch memory that hasn't previously been used. That can be a real-time hazard. And likely that the fact that executable code is fetched from disk means that you get unpredictable latencies even trying to execute pieces of code. This is an important aspect of mitigating real-time. It's one of the reasons I wanted to talk about user space in quite the depth I have, because this key to understanding things tells us about additional steps we have to take to make sure that our real-time processes stay real-time. And the typical technique that we use is called memory locking. We lock pieces of memory into RAM so that they cannot be discarded. We can force the kernel to load all the code into memory by memory locking. We can force it to allocate real RAM to all the components that we want it to have real RAM associated with. And then we can guarantee, because we've locked it, that it won't be discarded, it won't be paged out. If we come under memory pressure and we need to swap anything out or page out read-only pages, it will pick the non-real-time stuff. It will pick that HTTP server instead of picking our control loops. So that's what we do. We use locking to solve the problem. And there's some simple APIs to do it. The first is mlock. Mlock basically gives you an address range and says, stick it into memory. So you can find the address of your text, you can find the address of your data, you can say lock it into memory, make it right. That requires quite sophisticated understanding of how your application is structured. And like I say, knowing the address that your functions are going to be placed at can be done with elf link tricks, but it's a quite advanced bit of coding. So we do have an alternative. It's called mlock all. Mlock all basically works on the entire address space of the calling process. And by that address space, that means the executable code, the read-only tables, read and write data, everything. So that's literally everything that's involved. Shared libraries will be there as well. So you can bring everything into memory and keep it there. We can run it a couple of ways around. We can use MCL current, which will lock all of the currently mapped stuff, but not anything you map in the future. You can even have locks that apply universally. So any newly allocated memory after we've made this call will also be allocated. And then we've got the opposite, unlock all, which undoes all that. The problem with mlock all is that it locks all. It does what it says on the tin. And if you get a bit overzealous, if you have a large application with many, many threads, each with their default 1 megabyte of stack, and you're running on a low memory embedded system, 256, 512 megabytes of RAM, you call mlock all, and you'll probably, well, say if you're lucky, you'll get this, which is the killer coming in and killing your network manager. If you're unlucky, you'll get that, which is the system thrashing around desperately, trying to find a piece of memory in order to continue. So the killer, both of these situations are signs of systems that are misdesigned. You don't tolerate the killer. The killer is a heuristic that's designed to keep a desktop system interacting with the person sitting in front of it. It's a debug tool, if you view it like that. It has no place in an embedded system. If you've got as far as the killer, you've already lost. So the difference between an killer and this doesn't make a difference. In both cases, as a real-time programmer, you have failed if you see either of these behaviors. So there is a way we can work around that, a way to avoid this grossly excessive memory locking, and that's called MCL on fault. So on fault will lock a page after it gets faulted in. So I talked about the initialization of the stack. It creates address space, but the page itself will only be allocated when you hit that point on the stack. So mlock2 with this flag, MCL on fault, can do that. So that allows us to lock everything in memory only when it faults, and for all things we can set the future and current flags so that everything gets locked only when it's faulted in. That's all very lovely. That does stop the overmapping. That means that in most cases you won't see the killer if you try and lock in this manner. The problem is we've still got some of the RT problems because of the startup. At startup, I can do all that, lock everything on fault, etc., etc. Unfortunately, when I use stack, when I use error paths, I've still got to fault them in the first time. So in other words, this allows us to be efficient, but it doesn't lock in everything we're going to need. So these are only...
Sorry, Daniel, just a quick time check. We've got about 8 minutes to go, and there are a couple of questions, just so you're aware, in the chat.
Oh, well,
yes.
There's nothing showing for me.
Oh, really? In the chat for everyone?
I don't see chat. I see Q&A.
Okay.
Oh, there's a chat as well. I see.
Well, we can take them at the end. I just wanted to make you aware.
Yes, it is possible I might choose to answer questions overrun and finish the material within the time.
Okay, sure.
So avoiding overlocking, this is a suggestion, but it's one you can do. So if you have a massive process like that prototype at the beginning I talked about, if you're testing it, you're seeing problems because of the inability to keep things in memory, you can use mlock to lock text and read-only data. That you can do by looking at things like ELF sections. They're all marked appropriately, so you can ELF is all in memory, so you can actually walk through the output of the dynamic linker and figure out how to bring text and read-only data into the mlock call. It's a tricky bit of code. You have to understand quite a lot about ELF, but if you've got a big prototype and you're trying to prove the prototype before you move on to splitting it out into smaller components, that's one way to do it. You should probably allocate stacks for real-time threads by hand. So you don't have to get pthread to create the stack for you. You can actually just give it a piece of memory. So you can manually allocate the stack. That means you can lock only the stacks for real-time threads and leave non-real-time threads without a locked stack. You can actually also use tricks like mprotect. So if you've tuned the size of the stack quite deeply, you've brought it down to a small value, kind of 32K, then you can use mprotect to create a guard page at the bottom so that if you use more than 32K, you get a segmentation fault rather than corruption. That's entirely optional, but if you're going to use heavily tuned stacks, it can be a good idea. Obviously, you have to mlock any data structures that are used by the RT threads, and then you can see if you've got it right. That's the key thing. You can use something like perf report to watch for faults. You can get the system up, you can get it running the real-time system, and then you can start looking for faults and auditing the faults and finding out if there's any big problems. Okay, so and for small processes, it's actually quite easy. So once you've got your well-composed real-time system, mlock all starts to make sense now, because the real-time stuff is constrained within just these two processes. It's one of the things that makes this a well-designed system, in addition to the robustness that you get from structuring like this. By having just real-time in this process, then mlock all is the right thing to do. Always. The entire of this process was real-time. The entire of this process was real-time. So now mlock all is not going to overlock, with the exception of stacks. So it's still the case that pthreads will have surprisingly large stacks, and mlock all will end up with the whole stack being locked. The simplest way to handle this would be to use pthread attra set size to set your control loops to appropriate stack sizes. I mean, it still gives you all the problems of measuring stack sizes and making sure they don't overflow. But once you've got it constructed like this, then mlock all becomes the best way to handle these things. Now I'm going to skip over poll select and capabilities. I'll leave you to read those. Those were largely to introduce the concepts of poll and select to people who haven't got a Linux background, and I suspect much more of this audience is coming from the Linux world and adding real-time, rather than the real-time world and adding Linux. So I can skip poll and select with a fairly clear conscience. I will mention capabilities just very briefly. Capabilities, things like using the real-time scheduler is a capability that you can inherit. So the default simplest way to experiment is to remember that root has almost all capabilities, and therefore you can experiment writing real-time applications as root. There are also reasons why you might want to stop that and split things out and use the Linux user system to divide the system and add security through the capability system, even if that means putting the real-time components, which often don't need anything other than real-time, into separate places so they're not part of the possible attack vectors. Linux capabilities can be used to do that. We can break up the things, and we have capsys nice, oddly enough. Capsys nice is what gives you the capacity to set a nice value that is negative or further than the limit. That same capability also gives you permission to put processes on the real-time scheduler. The assumption is if you can be hostile enough with nice to dominate the CPU, then you can also use the real-time scheduler. That's fine. And there's other activities you can do, moving pages, IO setting, migrate, and so on. So you can read exactly what it's doing if you need to, but the key things we get from capsys nice are being able to boost the nice level of tasks and to be able to use the real-time scheduler. I'll come back to the CPU affinity because that's the answer to one of the questions that's pending. And finally, if you've got a real-time, once you've divided your system up, you need to get it running. Systemd is a common way to bring systems up and to set all the daemons running. In the case of an industrial control system, the control loops will be part of probably a systemd service somewhere. So we can do this with systemd. We can say run it as a particular user and force, allow that non-root task access to these capabilities. So that's just a thing to observe. If you want to switch away from using root for all your real-time activity, systemd provides you a really elegant integration of that. Yeah, I can do control groups briefly. So final thing I want to talk about is control groups. So control groups also provide a strata for constraining and controlling processes. Classically, they can provide security limitations, prioritization, accounting. There's a lot of different things that control groups can be used for. In the case of real-time, they can be used to split out the CPU that a particular control group may use. So we talked before about having that 100 millisecond window and 95 milliseconds reserved for real-time. Control groups allow that to be split across multiple different control groups. There's two reasons we talk about it at this point here. The slide up here is actually explaining to you why systemd is going to stop you creating user space, to stop you creating real-time threads, even if you've got the capabilities correct in user space. It's fine if you've used the essentially the way systemd constructs things is you've got system slice, which consists of all the services, and the user slice, which consists of sessions. When you log in, even as root, you'll be in the user slice. And unfortunately, the user slice has not been allocated any real time to it. So it has no real-time budget. The entire real-time budget sits in the system slice. The effect of that is that when you're experimenting on real-time systems with systemd and you've got a couple of kernel options set, is you can't create real-time threads. This is why I bring it up. So there are a couple of things you can do. You can, in the case of systemd non-root tasks, you can actually create and provide additional resources to it. I'm just looking for the summary. Yeah, sorry. So this is what's going on. You have a C group controller that allows you to set the runtime and the period just as you did before, and it allows you to set RT groups that are structured in particular ways. One thing I can do on the groups is control the affinities, which I think is one of the questions actually, which is quite convenient. Once you're split out into C groups, the groups themselves can have CPU sets associated with them. It allows you to do something like this, which creates a single CPU group that has been given all of the real-time budget and only one CPU, and then you can run non-real-time activities on other CPUs. C groups is a really good way to structure this. But the other thing is this inheritance of RT runtime and RT period. By default, these do not inherit. You have to give them to other C groups. And the default is that the login shell will not have any real-time time. So this is that last warning in the course. I know I've rushed through this last section, but this is the key message for people who are experimenting and want to actually get something done to start off with, is that if you have enabled config RT group shared and you boot with systemd, then by default, it's actually neither the user slice nor the system slice nor their children by default have any real-time bandwidth. That means that your console sessions can't start real-time things because there is no runtime period. Sorry, there's no runtime available to them. Your daemons can't start things because they have no runtime allocated to them. So if you've got both of those things present, systemd and RT group shared, then you have to make sure that you configure post-boot the resources available to the two slices. You have to split between the user slice and the system slice how much runtime you want to allow each to have. Obviously, during experimental phase, you give all the runtime to the user slice, and then you can do interactive experiments at the terminal. When you go to turnkey systems that boot up, you have to arrange for the runtime period to be handed to the system slice and then down to children. Otherwise, they will not be able to operate correctly. So that's just a major warning, I guess, about C groups. So we have some lab sessions coming through, which you can experiment with to learn more about it. There's also this real-time checklist, which is a rough summary of the various ways you can get things in the user space wrong. Just before I move to the questions, the last thing I wanted to bring up was the memory, yes, locking memory experiment. Yeah. So the locking memory lab has confused a few trainees in the past. It's basically trying to help you understand when memory gets allocated. I've asserted that the stacks and other things don't get allocated until you actually either lock the memory or use the memory. And there is a single test program here in C, in part of lab 3, that does exactly that. It basically allocates memory, a megabyte at a time, and then uses memory. And in our case, we're just doing that in a loop until the killer comes in and destroys the system, which we can do quite comfortably because we're running on a virtual machine. And the key question is going to be, at what stage in the code does the killer come in? Is it when we allocate the memory? Is it when we use the memory? Is it when we lock the memory? So the ambition is that you read the 5 different cases that we have. You look at what's happening inside the loop. When is it allocating? When is it locking? When is it using? When is it freeing? Sorry, it's never going to free. When is it locking? When is it using? And you predict at what stage in the cycle the killer will come in. It doesn't matter. It's going to run a couple of hundred times before it fails. The question is not what iteration will it fail at? It's at what stage of the loop does the killer come in, because that's the point where we've actually allocated the memory. So that's the essence of that lab. You're going to deliberately break your system, and the question is, after which system call is the system going to break? And that's going to help you understand exactly where memory gets allocated. Okay, so the questions that come in: tools to arrange groups of processes to schedule across multiple cores. So I take it that was a question related to the deadline scheduler. So with the earliest deadline first, I have not studied exactly what it does if you constrain the affinities. So yes, you can control what they will run on. And more than that, you can change what they run on after something's been accepted into the scheduler. So yeah, I have to say, I would have to run tests, much like the malloc test I've just shown you, to understand exactly what the deadline scheduler does at the point you make the system unschedulable. One thing that is known about the current entry algorithms is they're conservative. So they will actually refuse systems that are technically speaking schedulable, but they can't prove are schedulable due to the SMP behaviors of the system. So they are slightly conservative. And that's an area of active research. How that sits alongside affinity restrictions, I haven't studied in detail. Timer FD. Yes, so Timer FD is a good way to essentially manage time. I don't actually know whether POSIX timers are built. I would have thought POSIX timers might be built on top of Timer FD, to be honest. So this will be as we were walking through the various different timers. To some extent, it was an API tour. And yes, it wouldn't surprise me actually if Timer FD is used by the POSIX timers under the covers, but I would have to double check and mention it perhaps next week. And then finally, I've seen a thing from Amit. Can you prevent unschedulable systems on a single processor? For deadline, yeah. I mean, the question that you asked, actually, I'll just make sure that everybody's aware what it was about what happens to the deadline scheduler's entry checks if you have restricted the CPUs on which certain tasks can run. And I think the answer I've offered is, I don't know, I'd have to run some experiments. But it is conservative, and yes, it will prevent, if you've got a single processor, it will prevent unscheduled. If you've got an SMP processor, it will prevent unschedulable things. It's just I don't know what happens if you interfere with that with aggressive affinities. Okay, are there any other questions coming in? Is Timer FD a sane choice? It will be system dependent. It certainly does not have any hazards because it comes in via Poland Select when it expires, I believe. That's the FD aspect. And that fits in quite nicely. The question then is when you use Poland Select, you are waiting for multiple types of event, and they're going to be brokered by a single thread. So for good real-time design, obviously, all the messages that are coming in that are going to be brokered by this thread need to have a similar purpose or priority. And if they don't have a similar purpose or priority, you would need to be using multiple threads to allow them to have different things. So that it will be a sane choice in circumstances where there is no need to spread across SMP cores, and all the messages being brokered by that thread that's using Timer FD is getting the same thing. if that's not the case, then either you would use more threads, and then things like simpler things like clock nanosleep and so on would become more sensible, simply because they can be spread across threads very naturally. And once you've got a single thread doing a single thing, simple sleep becomes the right thing to do. So it's not that it's a hazard for RT. If it's the right thing for your design, it's certainly not hazardous or complicated in the way that signals are. But a lot of the APIs of the family of things like timer FD and so on are really good in a non-real-time world. I mean, if you want to have various timers, you want to wait for multiple things at once in an event queue. If you want to make optimum use of an SAP system, you only want 4 threads, and then you want to listen to all of them for events. That's where it kind of makes sense, where you've got pooled resources, and pooled resources don't make such sense in the real-time world where we're trying to be as fast as specified. So it's absolutely not a hazard. It's not wrong. It's not a bad choice. But the question is, what circumstances is it motivated? Because, as mentioned, things like timer FD allow you to have multiple SMP cores waiting on queues and reacting to different things, which is much more opportunistic, bandwidth-based activity rather than real-time decisions. Does that make sense as an answer? It's definitely not wrong, but I am struggling to construct cases where I would choose to use it because I haven't got that particular problem in front of me at the moment. It's similar to the reason that I skipped select and poll earlier, actually. So select and poll are brilliant APIs. They are absolutely great. They wait for multiple events with a timeout. That's a really powerful thing for running event dispatch. But the nature of event dispatch is, if you've got events of different priorities, it doesn't really work. You have to split it out by thread. So they're terrifically useful APIs. They're fundamental for every efficient server on a Unix system. Every efficient daemon has either select poll or epoll at its heart. But the reason I kind of skipped them in this case, partly for time, obviously, but additionally, situations where you've got lots and lots of events will happen. They will happen, but they're not as common as the single thread, single activity model. Okay, so last thing before you today. Okay, so can the scheduling policy be changed dynamically? Yes. So 2 of the APIs that we looked at, as in they can be changed after you've started things running. So, oh, it's a long way back, isn't it? So we have both pthread set shed param and shed set scheduler, both of which change the policy of a running thread. Now, clearly, to change dynamically, something has to make those API calls. So nothing in the kernel will dynamically switch you between modes. Once you've got a policy, you've got a policy, but user space, providing it has appropriate permissions to manipulate the process that it's changing, has the capacity to implement some kind of dynamic changer. Similar to the last question, why would you wish to dynamically change policy? The one that makes most sense for me is to allow a thread to do its own memory initialization and to clearly separate malloc done without permissions, without real-time case, and then you switch to real-time. And that would work nicely with profiling, because if you want to set a quality guarantee that you never fault while you are a real-time process, then it allows you to have a process. It can allocate memory, it can do all sorts of work, then it can change its own scheduling policy to real-time. And then if you've got something monitoring faults and checking which thread they come from, and then checking whether that thread was real-time or not, that quality of service monitor to observe that you never get unexpected faults would be able to do its job. It would be able to use the state of the scheduler to make those decisions. So that's the most obvious use I find for dynamic changes of policy. again, I don't pretend I have sufficient imagination to conjure in my head every real-time system in the world. But that's the one that resonates with me. I can't think of other reasons to be doing dynamic policy changes. So that's it for me. Apart from this support at linaro.org, everybody in the room today should be from a member. That means everybody in the room today has access to LDTS, which is the service behind support at linaro.org. So if you have any further questions that come up now or in the future about anything you've learned today, or in fact anything else that Linaro works on, this is an address I would strongly encourage you to email. I will see it certainly for the foreseeable future. If it's questions about this course, I'll pick it up and answer them. If it's questions about other parts of Linaro, some of my colleagues might get involved in answering your questions. But yes, keep an eye on that email address, keep hold of it. If you have any questions about what we've talked about today, that's where you can go for anything further that you want to discuss. So one last thing, we have made sure that we've got the link to the slides in the chat. Yes, so the lab material relies on downloadable components from here. That's where you can go to get those downloadable components. You can complete the activities. Oh, I'll update the lab activities. I think they're actually slightly out of date. So the lab activities were set up by somebody else. I've only just seen them. This link will definitely work. Has it been updated? Yeah, that's actually the better one. Yeah, I'll chase those up. I'll make sure that's updated and correct as soon as possible. So thank you very much for spending time with me today. Next week, we will look at both slightly more details about how CFS does its job, and then we will look at preempt RT in particular and the changes it makes to allow real-time systems to be more deterministic, better capable of meeting those guaranteed behaviors that we need. So, Ebba, is this the point to close things
yes.
down?
If you're happy, and we've answered all the questions, thank you everyone for joining, and see you